All right, 7th graders, we are in the high school book, section 6.3, over exponential functions. So, what are you going to learn? Well, here it is. You are going to learn how to identify and evaluate exponential functions. You're going to learn how to graph exponential functions, and you're going to learn how to solve real-life problems involving exponential functions. This section is quite long, so let's go over these step by step. Identifying and evaluating an exponential function. An exponential function is a non-linear function. That means it does not form a line. This does not form a line. And it must be in this form. Y equals a times b to the x power, where a cannot be 0, because if a was 0, you would just have a straight line. B cannot be 0, or b cannot be 1. The reason why b cannot be 1, because if b was 1, 1 to any power would still give you 1. Therefore, this would just turn into a number times 1, which will also be a line. B has to be greater than 0. So an exponential function, b has to be greater than 0. Make note of that. A cannot be 0, b cannot be 1, and it has to be greater than 0. So it could be like it could be like 1/2, 1/4, and such, but it cannot be 1. It could be 1.2, 1.1. As the independent x variable changes by a constant amount, the dependent variable y is multiplied by a constant factor, which means consecutive y values form a constant ratio. Here's what this means. If you were given something like this, what's happening? Let's get rid of the 2. I'm going to make this even easier. If you had this, 3 to the x power. If you had 3 to the x power and x was 1, you just have 3. If you had x as 2, it'd be 3 times 3. If we had another x, so if the x was 3, it'd be 3 times 3 times 3. If it was x to the 4th, it'd be 3 times 3 times 3 times 3. This is tripling every time. You are multiplying by a constant factor. In this case, the constant factor is 3. It's tripling every time. So let's do example number 1. Does each table represent a linear or exponential function? So we want to determine, does it make a line or is it exponential? So here's what we need to look for. Linear, you're going to be adding or subtracting by the same number. Exponential, you're going to be multiplying by a constant factor. So if we look at, for example, the first one, each x value goes up by 1. Okay, so far so good. This goes up by 2, this goes up by 2, this goes up by 2. Therefore, since you're adding each time, it's just going to be linear. We would say in our answer, I want answers that look detailed like this. As x increases by 1, y increases by 2. The rate of change is constant. Notice the slope on all of these would be just 2 over 1 or 2. Therefore, the function is linear. In the second example, your x value also increases by 1 each time. So you could say this increases by 4, this increases by 8, this increases by 16. But let's look for the pattern. This is actually times 2, times 2, times 2. Therefore, that's going to be exponential. So as x increases by 1, y is multiplied by 2, so the function is exponential. Example 2 is quite easy. We're just going to evaluate each function for the given value. In A, we have y equals -2 times 5 to the x power, and x is to the 3rd power, so x is 3. So remember to follow order of operations. We would take -2 times 5 to the 3rd power. 5 to the 3rd power is 125. Do not take -2 times 5 first. That would not be following order of operations. So your answer would be y equals -250. In B, we're going to plug in -2. And if you did that, you would get y equals, well, 0.5 to the 2nd power. I'm sorry, that's to the -2nd power. That would be 4. And so your answer would be y equals 12. The next thing we're going to talk about is graphing exponential functions. Now, the graph of a function that's in this form is a vertical stretch or shrink by the factor of the absolute value of a of the graph of the parent function. Make note that this is the parent function. Remember, the parent function is your original function. So if b was 7, your original function would be y equals 7 to the x power. If your b was 5, it'd be 5 to the x power. So it changes depending on what problem you have. When a is less than 0, the graph is also reflected in the x-axis. The y-intercept of the graph is also this. So the y-intercept is always just what a is. Here's the reason why. The y-intercept, if you remember, is when x is 0. So if you plug in right here for 0, anything to the power of 0 is 1. So this just becomes a times 1. So whatever a is what number goes there. And that should be an a. And that looks not like an a. So let's change that to an a. So here's what it looks like. If you graph when b is greater than 1, so this is important, think about this. b is the number that you're multiplying by every time. So if you multiply by a number greater than 1, your line is going to go up. So whoop, up. Now, it only goes up though if a is a positive number. A is greater than 0. If b is greater than 1, but then a is negative, it's just the opposite. It reflects across the x-axis. It goes down. Now, if b is, remember, b has to be anything but 0 or 1. So remember, b has to be greater than 0, but it cannot be 1. So if b is between 0 and 1, that means it's a fraction less than 1. If it's a fraction less than 1, think about what happens when you multiply a repeated fraction. 1/2 times 1/2 times 1/2. 1/3 times 1/3 times 1/3. It gets smaller. So if a is positive and b is between 0 and 1, it goes downhill. But then if a is negative, it reverses across the x-axis. It's reflected. So please make note of all this. There's a lot of stuff here. Now the last thing I want you to look at is this. Study tip. I'm going to put it down here. The graph approaches the x-axis, but it never touches it. So notice this, that all of these lines look like they're going to hit the x-axis. They don't. Example 3 is just graphing. So when you graph f of x is equal to 4 times 2 to the x, you're going to compare the graph to the graph of the function and then describe the domain and range. Now, I'm going to tell you right now, you're going to make a table of values. So if I made a table of values, x and y, I'm just going to write them down here. I would always pick, this is just a suggestion, I would always pick 5 or more values. Where one of your x values is 0, pick 2 numbers less, pick 2 numbers above. You don't have to, but that's what I would suggest. If I plugged all of these in, you would get all these numbers. That's just simple math. And then all you do is graph it. Now remember, the parent function is this. It's y equals, remember this is a, this is b, so it's y to the b to the, y equals b to the x power. So that's the parent function. So we have to compare and graph it. So if we graph it, here it is. The blue line is f of x equals 4 to the times 2 to the x power. That's if we graphed all of these. Here is g of x equals 2 to the x. That's our parent function. So describe the domain and range of f, and we have to compare this graph. Now I'm not going into detail how to graph these because you should know how to make a t-table, plug stuff in, and graphing this is not hard. You just graph your dots and then make your line through it. But make note of this. This is your asymptote, which we'll learn later. This is where your line will never touch the x-axis. It'll look like it's getting close, so make sure you draw it going down but not crossing. So here's our parent function. The parent function of g of x equals 2x. So we want to know, compare this to this. What's the only thing that's happened? It's been multiplied by 4, so that's what you'd say. The graph of f is a vertical stretch. You'll notice that because a is greater, it pulls it. It makes it stretch. So it's stretched by a factor of 4. All you do is multiply by 4. The y-intercept of the graph of f, so here's f, is 4, which is above the other one, which is of g, which is 1. So we compared two things, the stretch and the intercept, the y-intercept. So that's all you have to do. Now your domain and range. If you look at your x is your domain. It's going to the left and going to the right. You can plug in any value you want to either one of these. So the domain is all real numbers. The range, however, it approaches what? It approaches the x-axis, which means your y value for the range always has to be greater than 0. So now we're going to graph when b is between 0 and 1. So you'll notice right here, first off, there's two things you should notice. There's a negative out front. Because it's negative, it's going to be reflected. And 1/2 to the x, which means if you multiply by 1/2 every time, it's actually going to start high and get lower. So we're going to make a t-table. There's a t-table that came out of nowhere, magic t-table. So if I use these values again, -2, -1, 0, 1, and 2, and plugged them in, you would get these 5 values. If you graph this, and the parent function. Now remember, the parent function is just taking the b value. So g of x equals 1/2 to the x power. That's your parent function. F of x equals negative times 1/2 to the x power is this red function here. So we have to compare them. Well, you would say first that the graph is a reflection. Because this was negative, a was negative, it's a reflection in the x-axis of the graph of g. So make note, we took g, and it's a reflection of that. The y-intercept of f is -1, which is below the y-intercept of 1 of function g. So if we look at the domain and range, now we just want the domain and range of f. I want you to make sure you understand that, just of f. So if we look at the red, your domain is all real numbers because the x value can be anything. But range is everything below the x-axis, which means your range is y is less than 0. Now this is how you translate an exponential function. This is going to be very similar to what you learned with parabolas. To graph a function that looks like this, now you're like, what in the world is going on? Here's what we're doing. Let me actually move this down. If you started with y equals ab to the x power, and you slit it either left, right, up, or down, it's going to change two things. This, which is going to affect if it goes left or right, which is that right here, and at the end, the plus k, whether it goes up or down. So, it says right here, translate the graph horizontally h units. Now it's backwards. So remember, this was just like what we learned before. If it's a +5, we're actually going to go left 5. If it's -3, we're actually going to go right 3. And vertically, k units. And this just means if it goes positive, it goes up, negative goes down. So let's graph. Describe the domain and range. Now when we graph, let's just get rid of all of our translations. So we're going to graph y equals 4 times 2 to the x power. We're not going to do this because right here this means I'm going to go right 3 and up 2. So if you just graph this, here it is. We just make a t-table. And you can do that on your own. The black line here represents if you would graph it using a t-table. Now, the -3, which is right here, that tells me to go right 3. The +2 tells me to go up 2. This number tells you to go vertically up or vertically down, and the -3 will tell you to go right or left. So notice what we did with every point. Here's our first point. I go right 3, 1, actually we're counting by, it looks like 2's here. So right 3, up 2. And then we took this one, right 3, up 2. Then we drew our new line, and there's our graph. Now the domain and range. Domain and range. Domain is all real numbers because I can go left or right. So the domain is all real numbers. The range though, let's do both ranges. The range of y equals 4 times 2 to the x power and then we'll do y equals 4 times 2 to the x minus 3 plus 2. What do you think the range is going to be on the original black line? Well, it's going to be anything greater than 0. So y has to be greater than 0. But your range on the second one, since everything shifted up to, notice where it's approaching. It's no longer approaching the x-axis, it's approaching 2. So that means, since we went up 2, your range has to be greater than 2. In example 6, we're going to compare exponential functions. An exponential function g models a relationship in which the dependent variable is multiplied 1.5 for every 1 unit the independent variable x increases. Graph g when g of 0 is equal to 4. Compare g and the function f from example 3 over the interval x equals 0 to x equals 2. So it's telling you right here, I want you to compare from when x is 0 to 2 on two different functions, g and f. So the first thing we have to do is make a table of values for x and g of x. So what does it say? It says right here, when g is 0, so when g of 0 equals 4, that means x is 0. So that means if x is 0, g of 0 is 4. So we know this. It says it's multiplied by 1.5 for every 1 unit the independent variable x increases. So all I do is this. I multiply by 1.5. 4 times 1.5 would give me 6. 6 times 1.5 would give me 9. If I went one more, 9 times 1.5 would give me 13.5. If I went the other way, I'd divide by a half, I would get 2.7. Now, example 3, which is f, that's from example, we already did that one. And then if I graph these, that would be function g. Now, what does it ask me to do? It asks me to compare in the interval x equals 0 to 2. So it's right here. Here's 0. Here's 2. So I want to know what happens in this window right here. You could say this. They both start at the same value. They both functions start at the same value when x is 0, or you can say they both start at the y-intercept of 4, but the value of f is greater than the value of g over the rest of the interval. That's it. Notice how f increases more than g. That's all you had to say. Solving real-life problems. For an exponential function of this form, the y values change by a factor of b as x increases by 1. So you can look at the example. You can use this fact to write an exponential function when you know the y-intercept. You must know the y-intercept, which is right here. The table represents the exponential function. Here's how you get it. If you start at 2, that's your a, that goes right here. This number, what the factor is that you multiply every time, is what b is. Example number 7. The graph represents a bacterial population y after x days. Write an exponential function that represents the population and find the population after 12 hours and after 5 days. Believe it or not, I find these much easier than graphing. Part A, we write it in the form y equals a times b to the x power. So we first identify what a is. Where did you start at? Well, it says right here, if we just made a table real fast, you start at 0, 3. The next order pair is 112, then 248, then 3, 192. So you just figure out what happens. Well, you start at 1, 3. So your a value is 3. Times b to the x power. B is what we're doing each time. So as x increases by 1, which is what we want, 3 to 12 to 48, well, you're just multiplying by 4. Multiply by 4. So that would be y equals 3 times 4 to the x power. So part B, we use that to then answer the question. Y equals 3 times 4 to the x power. Y equals 3 times 4 to the x power. Now, right here it says x is days. So find the population after 12 hours. I wouldn't plug in 12 for x because that'd be 12 days. What fraction of a day is 12 hours? It's 1/2. So if you solve this, 4 to the 1/2 power is the square root of 4, which is 2. 3 times 2 gives me 6. So this would mean there are 6 bacteria. And if I solve this one, it says 5 days, I plug in 5. That would be y equals 3 times 1,024, which would give me y equals 3,072. So then after 5 days, there would be 3,072 bacteria.